Okay, so now we'll start again with the microphone on. So, uncertain system 01, new project. Basically, what I'm gonna do is I'm gonna try to build an LLM from scratch, just to learn how these things work under the hood. What I was saying now, before I realized my microphone was off and I started the recording again, is that it's the first time really that I'm playing with something, with a piece of software where the sort of the result, it really doesn't feel like the sum of its parts. You know what I mean? This kind of was a similar moment with Grover's algorithm and what got me into all the thing with quantum computing. It's like, and then later on in general with this kind of concept of uncertain systems, is that it really feels like the result of what you're interacting with is not, it's more than the sum of its parts. And that's kind of what's amazing, right? So, and then the thing is with quantum computing though, when you dig into these deep enough, you realize that there's this concept of entanglement, which in a way is what justifies, or it seems to be at least the first little step to understand why these systems seem like, you know, more than the sum of their parts. Because when you entangle two particles, you can't talk about each subsystem separately, but you must talk about the whole system. And it doesn't explain it, but it doesn't explain why, but it in a way makes sense that you have that piece, that building piece that is like, when you entangle, you can't talk about the two systems independently. So you must talk about the whole full system at all. But that's physics, that's quantum physics. And in this case, we're dealing with software. I mean, at the end of the day, there's code, there's just pieces you glue together. So I'm trying to see if I can find that entanglement, you know, I can find that kind of like piece that doesn't necessarily explain why you feel like that about these models, but at least that it somehow gives me a feeling of like, oh, okay, so that's a piece that's a bit odd. That's kind of what's different from just like, you know, traditional programming, you know what I mean? So this is what we're going to try to do. It's going to be a long project, and it might just take the rest of the year. That's fine, but let's just get into this. Let's build an LLM from scratch. It's definitely going to be inefficient. It's definitely going to be not ideal. I don't want to use any of this stuff. Then that's going to be probably a follow-up, I guess, of see what things can we use from existing libraries. But let's just go ahead. So now I'm not so sure how powerful Ghostwriter will be here. I'm going to try to stick to Ghostwriter, just because I have the feeling it's getting more consistent results if you stick to one of these conversational partners. And I don't really have access to GPT-4, so I think GPT-3 anyway doesn't really make much difference. And GPT-4, maybe I'll go for like a month and then see if that brings additional help. If I get stuck, maybe we'll see. So how do we do these? So okay, so let's make a plan. Okay, what is the first thing to implement? Let's do when it comes to sort of a transformers architecture for an LLM. It's going to be a small language model, probably. The first step in building a transformer architecture for a language model is to pre-train it on a large corpus of text data. But that's wrong. Okay, so pre-training steps can be written as mask language modeling. In this phase, the model is trained to predict the missing or masked words. Next sentence prediction. Okay, but I'm talking about actually writing software and without using any existing libraries. Defining the core components of the model, such as the multi-head. Yeah, so let's just go component by component. So the multi-head self-attention layers, feed-forward neural networks. You need then to You would then initialize the model's weights and biases and train the model using backpropagation and gradient descent to minimize the loss functions such as cross entropy loss. There's some basic steps for writing a transformer model from scratch. Initialize the model's parameters. It definitely it helps me, I think, understand some of the. Okay, can you list all the modules or components that we need to implement? That sounds like an easy one to start with. So positional encoding, this module is used to encode the position of each word in an input sequence so that the model can learn how to attend to different positions in the sequence. So that seems like a small starting point. I'm not, let's just jump into it. So let's start, okay, cool. So let's, my assumption is Python is the way to go. So to be honest, I don't know. So let's start with positional encoding. Let's start with one. Can you give me a base implementation? So torch tensor, torch. Can we implement it without using any libraries like PyTorch and TensorFlow? Maybe that's too harsh, but like I wanna make sure that we're not really doing some kind of magic that you know, that maybe hides or abstracts away that complexity that we're you know, whatever we're looking into. So let's put these in here. What do we have? So we have positional encoding as a class. We initialize it with what is D model max length. So can you explain the initial? Can you explain the parameters? Can you explain me the parameters? Here. So as a size. So this is the size of the embedding dimension. In other words, it's the number of features used to represent each token in a sequence. Like the token is, I believe. So what is a token? So what is a token in this context? I believe this is either the word or a letter or half of the word or something like that, right? The unit of data that's being processed by natural language. Okay, so a word, subword, character, exactly. Yeah. So this is the size of the embedding dimension. In other words, it's the number of features used to represent each token in a sequence. So okay, so the number of features used to represent each token. It's an integer, and then max length. So the number of integers, So what would these features be? This is the first question I have, right? So embedding dimension, the number of features to represent each token. So let's say if a token is a word, I guess that defines what the word is. D model is D model used in here? So 0. So compute the positional encodings before training. So it seems like it takes a matrix of zeros. Add a patch dimension to the positional encoding. I have absolutely no idea what's this doing. So PE is positional encodings. So this is the max length, it's the maximum length of a sequence for which positional encodings will be generated. The positional encodings are generated using a fixed set of weights. So the maximum length of the sequence determines how many unique positional encodings will be used. Okay, so so this is the, I guess this basically defines how many, sort of the length of so how many symbols you want to be able to reference to at any given time. The positional encodings are generated. Positional encodings. So this is P. So what are positional encodings used for? Okay, so this is basically information about the position. Talks about not their absolute position. Without positional encoding, the transformer-based model would only have access to the relative position of tokens. And again, let's be aware that, you know, whatever Ghostwriter is telling me might just not be completely accurate. So I have to try to be self-critical or critical in my thinking every time I'm reading this stuff, because I'm not so sure what he's saying is correct or not. This could lead to problems with long documents treated as if they were interchangeable. Tokens to improve the quality of its predictions. Okay, so the purpose of positional encodings is to provide positional information to the input sequence. So you have this, you have basically you have this input, and you can treat these as symbols, and then you need to basically encode their position. But how is that then working here in this PE? So can you give me some code to test the class we've created? Okay, so let's just keep here some testing code. So what do we have? So we import, so NumPy is already imported, that's fine. You create a positional encoding for a model with, what was the model? Was the okay, so this was basically the dimensions. This was basically, it's all quite abstract. So this is basically the size of the embedding dimension. So in other words, number of features to represent each token. So we're going to run each token with 512 dimensions. I don't know. Create a random input. So create a random input tensor of shape. So you have an input tensor. Apply the positional encodings to the input tensor. Print the shapes of the input and the output tensors. If I run this, tensor shape, but what does the input and output? So I guess this tests that position encoding. What is these? What is that even from? Why does this even work? Where is this defined? Def call. Oh, okay. So what is that? I have no idea. This is the first time I see that. That's going to be very challenging. So output tensor. Oh my god. Okay, so you're calling the yeah, sorry. So you're using that. I've never done that. So you can use these as you can call these like this. Okay. So you add the positional encodings to the input tensor. Okay, but what's the purpose of these? Positional encoding. So what's the purpose of positional encoding? Just to give these things. So can you explain how? Let's see if I can explain what's going on here. This big. So this code generates the positional encodings for the transformer model. The cost starts by creating a matrix of zeros. Yeah, okay, that I understand that with this shape. It's the maximum length of a sequence. And the amount of the size of the model's hidden state. Is it the size of the model's hidden state? There's a lot of conceptual stuff that I have to actually still connect. So we then loop through each element in the matrix. Okay, so it's just a matrix, right, of max length. So essentially you have as many entries as symbols you want to have, and then each symbol has the features, right? So the outer loop iterates over the positions in the sequence. So what is the outer loop? So that basically, of course, that's max length. So that's then the input sequence you have, the input tensor, a random input tensor, exactly. And so that's we'll get into this, but I guess that's what it, so that's a way to model the different 1,000 tokens that you have. The inner loop iterates over the elements of the hidden state vector for each position, and each element will compute the corresponding value of the positional encoding using a formula. The formula is different for even or odd values. Because even we use a single sine function. If I always a cosine function, the formula involves raising. Why is that? It depends on. Okay, so that's just to generate a unique value for each element in the hidden state vector. These values are added to the P matrix to create a final positional encoding. Oh wow, okay. So interesting. So we are essentially, what we're doing with this is we're encoding, we're giving an encoding, a unique encoding to each element in this. I guess that's what it's doing, right? So we're saying we are giving a to each element. Let's say I have a string, and no, I have like a set of symbols that's my like input, and then we're basically encoding. So for each of these symbols, we give it a unique. This formula is just to give it a unique representation. A unique sequence of 512 elements. I don't know why you do that this way though. Once the positional encodings have been computed, they can be added to the input embeddings. So this is what's happening here in test code, right? Add the positional encoding to the input tensor. So you have you literally add them. Okay, so you literally you're literally adding this positional encoding. Okay, so I think what this is essentially making sure is that you okay, I think I'm getting it. So you generate an encoding that is unique for each position. I'm not so sure why the sine and the cosine are good choices, but you generate for each position. There is an sort of a number that you generate. Well, in this case, I don't know if it's a number. It seems to be. It's basically 512 in this case, dimensions, whatever numbers. And then you, in your input tensor, which is what, 10 words, and yeah, and each, or 10 tokens, and then each token is a this is the sequence. Explain code. That's nice. Okay. So it explains. So you basically have a batch size, whatever that is, and then you have sequence length, and this is, I assume, it's just a random. So you just have basically 10 tokens, and then each token has 512 elements, and then you're just saying apply that. So you take you basically for and I think that's basically looping. I don't know I'm not familiar with them. With the notation, but I'll ask it in a second. And essentially, I think what this is happening is you're just basically adding these, you're padding these inputs, or you're adding these values to your input. So essentially, if you, because if you have a token that represents the word tree, right? These will be then essentially given a final number or final representation, depending on where it is in your sequence, right? So the order actually matters. Otherwise, the word tree for the model would mean the same, regardless of where it appears in your sequence, which obviously makes no sense. So I think that is, okay, so I think that's really what's happening here. I'm not so sure why you need the why you need the model. Why do you need the model? Why can't just be one? So it cannot be one because the purpose of the positional encoding is to add information about the position of individual elements in the sequence to the input embeddings. This positional information is critical in enabling the transformer to better understand the structure of the input sequence, and it improves the accuracy of the model. In order for the position encoding to be effective, it needs to be able to represent positional information with sufficient granularity. Exactly. If the model were to set 1, then each element positional encoding would only have a single value, which would not be sufficient to encode position information for sequences longer. But that's not true, right? Because essentially you're generating so max length is just the positions that you're, and then for its position there is basically which position encoding which only have a single value, which would not be sufficient to encode position information for sequences longer than one element. I don't think that's true. In practice, it's typically set to value depending on the application and the size of the input sequence. It is important to choose an appropriate model value for a specific application to ensure. Yeah, but essentially, sequence length. Can you give me so? Can you print this code? Exactly. So D model 4, max length 5. Exactly. So each row a position. Correct. in the positional encoding array, each represents a position in the input sequence. This means the first response to the first position. So exactly. So why do we need these rows? I know the answer is granularity somehow. I know, but I'm not so sure I understand. Cannot you just represent each position with a number? You know what I mean? So why do we need these rows to have dimensions bigger than 1? How does this improve accuracy? Because the hidden state vector for each position in the sequence is a multidimensional vector. Okay, so the hidden state vector for each position is a multidimensional vector. The position encoding allows the model to distinguish between different positions in the sequence by encoding information about the position of each element directly into the input embeddings. This helps the model to better capture patterns and dependencies that exist across the input sequence. If we were to use a one-dimensional positional encoding vector for each position in the sequence, there would be no way to encode information about the position in multiple dimensions. Okay, but fine, but why? Okay, so by using a multi-dimensional encoding, it allows the model to be more efficient, to more effectively distinguish between different positions in the sequence, which can help to improve accuracy. The state vector, so it basically says this helps the model a state vector of each position in the sequence is a multidimensional vector. So you said this. Can you explain why we need to represent each input token? I guess it's just maybe representability, isn't it? Yeah, I think it's just because you want to have as many possible token representations as possible, so you need multi-dimension. Like if you just use an integer, then you know that's got its limit, right? So in natural language processing, a single word in a sentence can have multiple features, attributes such as the pattern of speech, a lemma form. Ah, okay, I get it. So essentially, we just say each token needs a multi-dimensional representation, because this essentially will be maybe features or just random, whatever it is. But you need, like, if you're just one-dimensional, then you're missing. I get it. Let's put it this way. So, for example, if you know, yeah, like there are words that can be used as adjectives, as subjects, as stuff like that, right? So if you just, I guess if you would use one number per word in the dictionary, to represent a token, then that would definitely be not accurate. So I guess that's what it's trying to say. And then essentially this means whatever you're using here in your input to represent, so the D model is something that you need your positional encodings to also have the same dimension, because what you want to do is you want to take that vector that represents each token and basically modify it, uniquely modify it to represent the position. Okay, I think that that's a good starting point. Makes sense. So positional encoding, I guess we can call, I guess it's okay. I guess it's done. I understand what's the purpose of the positional encoding. I'm gonna assume that's correct. Currently, I don't know. Let's see. I don't know yet why this is a good way to generate those uniquely. I guess it makes sense, like, that you're using sine, cosine, because they're somehow, like, you know, they just have a phase difference, and then yeah, but I don't know if this is something that is just, I guess there's different ways, different things you could plug in here in a way, right? And then the next step will be to implement the whole thing with the attention. The tension scores, because essentially what we're going to do is we want to be able to have a model that you give it an so you give it you have an input, and then you kind of get the prediction sort of what are the next characters, right? let's just stick to this goal initially, and then let's see where we can take these. Now my question is like, will you use conversation next time I open the project? Because I might as well just, can you give me a transcript of today's chat history chat? Because I might as well just put it here, transcript, and today is 27 March. So essentially transcript. I mean, yeah, how you can always reference the conversation history in the replay ID as well as save the conversation locally on your computer. Can you? So I can save it. I don't know if it's gonna be. Okay. Too long of a conversation, I guess. Anyway, I'll do that before I close the project, and then we get started next day with these. Come on. Hello? Can you give me a text summary of our conversation today? That's not, no, that's not. Can I, what if I, okay, so what if I just do these? If I copy paste it in here, okay, I think that could just be enough. Ideally, I love, yeah, let's just use that. Save that. Can you read? No? I'm sure they can. I'm sure it can. Anyway, at least we have the transcript in here. So see you next time.